Welcome back for another episode. Today, you'll find that some assembly is required as we head into Day 7 of Advent of Code 2015. Be sure to check out the problem at the link in the description and sit tight, as today's problem is one of the first that might be a bit longer and more tricky than before. Let's get started. This year, Santa gifted little Bobby Tables a set of wires and logic gates. Since Bobby's a bit too young for this, we need to help out. Each wire has a string as identifier, lowercase only, and can carry a 16-bit signal. This means that the value can range from 0 to about 65,000. Each single wire can only get a single signal as input, but it can output a signal to multiple destinations. The included instruction booklet describes how to connect parts together. For example, suppose that we have an AND gate that takes in wire X and wire Y and outputs the result on wire Z. Then we can visualize that as shown below. If we ignore the instructions for a second and we just take into consideration that they shall be combinations of wires and logic gates, then the question is as follows. Given a set of instructions, what signal is provided to wire A in the end? At this stage, it already becomes clear that we shall be dealing with a network of wires and nodes, and we shall have to simulate the values as they propagate through the network. So let's have a look at the possible instructions. Firstly, it can be that the value of a wire is set directly. In this case, we assign 123 to X. Then, of course, we can also have an instruction with an AND gate. It takes in the values from two wires, in this case X and Y, and it puts the bitwise AND of these two as the output on wire Z. I won't do a full refresher on bitwise operators in this video, but please have a look at this example. Suppose you have the values 21 and 6, then applying the logical operator means that only the bit indicated with the green line gets put on the output wire. Thus, the value of Z in decimal or base 10 would become 4. Next up is the L-shift instruction. It takes in some wire, suppose it's named P, and a constant value, in this case 2, and it shifts the value of PI 2-bit positions to the left accordingly. If you are unfamiliar with this, then please take a moment to take in the example below. Another common gate is the NOT gate, which propagates the bitwise complement of wire E onto wire F. In the example, the number of bits is limited to 8. See how all ones are turned into zeros and the other way around? The last two remaining instructions are the OR gate and the R shift. They are conceptually very similar to the previous instructions. Should you at this point be unclear about how binary and binary operators work on a fundamental level, then it might be a good idea to pause the video and refresh your learnings on this topic. I don't have videos out on this yet myself, but plenty of resources are available on YouTube already. We're a bit in luck, as we are gifted a single example which covers all possible instructions. It looks as a graph where we set two numbers on wires X and Y, and then we have various outputs. We shall have a closer look at one of the instructions, but first let's see the answers. Now if we zoom in on the NOT gate, then we can have a nice example to remind ourselves that we should work with 16-bit numbers. Here we can see that we put 123 to wire X, and then we put NOT X onto wire H. If we consider the 16-bit representation of 123, then we see 6 bits are set. For convenience, I grouped the numbers in chunks of 4 bits, but in practice, they're of course a single binary number. Now, if we flip all the bits, which is what we do with a logical NOT operation, then we get the answer which we were looking for. Again, note that having 16 bits is critical here. If we would only consider 8 bits, then we get completely different results. The first thing to realize is that the instructions describe a directed acyclic graph. Maybe you already figured it would be a graph, but why is it acyclic? Well, if it wasn't, then there's no way to guarantee that the output on wire A would be stable. Cycles could introduce feedback loops which continuously change the values on certain wires. So it is pretty safe to assume that the author of the problem is nice enough for us to make the problem deterministic. The next step, then, is to deal with two important implementation aspects. The first being that we need to visit the nodes in the correct order, which shall be the topological order. Secondly, we of course need to implement the wire and node logic correctly to propagate those 16-bit values from wire to wire. Let's start with tackling the first challenge, visiting the nodes in topological ordering. For this, we can use Kahn's algorithm, but why do we even need to visit in this order? Well, it is important to realize that before you can process a node in the graph, all of its inputs need to have been processed as well. Logically, this then means that we can only ever start processing the nodes in our graph, which have no parent, or incoming wires, if you will. Let us visualize this in the graph below. Suppose that we want to process the node marked with a star. Then all other highlighted nodes must be processed by our algorithm first. So for our algorithm, let's give every node a number which represents the total number of parents which still need processing. On the left, you can see two nodes with value 0. They have no incoming wires. Then there is one node with a value of 1, and there is a single node with 2 parents. Though I did not mark it in the graph, the starred node, of course, would also have the value of 1. With our algorithm, we can put all nodes with value 0 in a queue, and then we go over one by one. For every node we process, we can update the children attached to its output wire and reduce their value by 1. If the value of a child is now 0, then we add it to the queue. Again, we iterate and update a child. We can reduce the value from 2 to 1, but remember that as long as the value is not 0, then we cannot consider it ready for processing yet, so we do not yet add it to the queue. Then finally, the second parent is processed and we update the value to 0. Now all that's left is to process this node and we can add the starred node to the queue. Eventually, as we continue through our queue, we'll encounter this node and we then compute what the value on its output wire is. And this is the gist of the algorithm with which we can process all nodes and wires in our graph. Here is some Python code which represents what we just did. It assumes that we have node objects which track the total number of unvisited parents, as well as the children within the graph. At the top, we start with a list which we will treat as a queue. The first thing that we have to do is to insert all nodes which have no parents, since these are the nodes that are already ready for processing. Then we make a variable named I, and we set it to 0. We use this variable to track which item in our queue we are currently processing. Technically, we are not using a real queue here, as we shall never pop any items from the front, but we can mimic the behavior of a queue by just tracking the index. So, we have I, and as long as I is less than the length of the queue, then we know we are not done yet with processing the graph. The trick here is that the queue will become longer and longer as long as we keep discovering new nodes. At some point, we run out of nodes to discover, and the while loop shall stop. Within the while loop, we first get our node from the queue, and then we can update the children. Here, we subtract 1 from the unvisited parents property, and if that is 0, then we add the child to the queue. In between getting the node and looping over its children is an excellent spot to put some logic related to processing the signal. At this point in the code, you know that all inputs for the current node have been processed, thus it should be possible to somehow get the values from your parent nodes or wires and calculate the output again. Lastly, of course, we need to increment I by 1 to move to the next node in the queue, and that's it. You now should have an algorithm which visits all nodes in the graph in topological order. The second part is implementing the 16-bit logic. Here, it can be helpful to realize that although every instruction has one output wire, there are 3 types of instructions in the input. Firstly, there is the NOT gate with 1 input. Then, there are 2 instructions with 2 wires as input. And lastly, there are the 2 shift instructions which take in a wire and a constant. Depending on how you write your solution, you could also consider the constants of the latter simply as nodes without parents that put their constant into the shift node via a wire. For the final implementation detail of today's puzzle, let's look at the 16-bit logic. The tip here is that numbers are usually represented with 32 or 64 bits instead of the requested 16, so we must crop them when applying operations to get the correct values out. Take, for instance, the example of this NOT gate. We set x to 123 and y to not x. When we print y, we get back minus 124. The details of why exactly this number is something I'll not cover today, but suffice to say that since the representation of the number is in more bits than 16, we are setting many more bits to 1 than we intend. To fix this, we can create a mask that consists of 16 ones. One of the easiest ways to do this, in my opinion, is to take 2 to the power 16 and then subtract 1. Then, if we take the same y as before, and we take the logical and with the mask, then we basically trim off the bits that we did not intend to set 1. Thus, they'll remain 0 and we actually get the answer which we were looking for. Hopefully, this has been enough detail to get you going on the solution without doing a line-by-line code solution. Let me know in the comments if you think this works or if you like more details. For now, I will move on to part 2 of today's problem. In part 2, we're asked to make a fairly simple adjustment to our solution of part 1. We computed a value for wire A, and now we just set this as the input to wire B, and we run our code again. What's the new signal on wire A this second time around? Let us dive straight into the solution. It, of course, all depends on how you wrote your solution, but in principle, the only change we have to make is in parsing the inputs. We have the same input file with the same instructions, but one of the instructions shall be different. And that's it. Thank you for sticking around in this more detailed solution, and I hope that you consider this to have the right balance between solution details and high-level understanding of the problem. Please consider helping the channel grow by liking and subscribing, and I look forward to bringing you more solutions like this in the future.